Okay, chapter 14, worksheet solutions. The first problem here, a calorimeter is completely insulated so no heat can be exchanged. It is made out of aluminum with a mass of 27.5 grams that is in thermal equilibrium with 125 grams of water held in the calorimeter. The water and calorimeter are initially at room temperature, which is 20 degrees Celsius. A 20-gram piece of iron that has been raised to 9 degrees Celsius is added to the calorimeter and it is sealed. What will the final temperature of the calorimeter and its contents be when equilibrium is restored? What will the change in entropy be for the system? So let's start just by interpreting this. Calorimeter. Calorimeter is simply a container that is completely insulated, so no heat can go in or out. So that means we can go right down to the second question. Calorimeter is insulated, so the net heat exchange inside the calorimeter is Q total equals 0. That's the key for a calorimeter. Now, the calorimeter has a mass of 27.5 grams that is in thermal equilibrium. Thermal equilibrium, we have that here for part A. Thermal equilibrium means that objects in thermal contact, that is, if they are arranged so heat can pass between them, they do not exchange heat. That's what thermal equilibrium means. You have things that are in contact with each other. They could exchange heat, but they don't. That occurs when they're at the same temperature. Remember, the 0th law of thermodynamics talks about if object A is in thermal equilibrium with object B and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. That's the terminology we're working with here. So we have water and aluminum, both at 20 degrees Celsius, and then a 20-gram piece of iron that is at 9 degrees Celsius is added to the calorimeter, and it's sealed. So heat can't be exchanged between the calorimeter aluminum iron system and anything else, but it can be exchanged between the things inside the calorimeter. So we're going to have three heats that we're worried about here: the heats for the iron, the aluminum, and the water. So in order to do this, we need to know what the specific heat or if you want to be really technical, it's the specific heat capacity for each material in use. So I looked these up beforehand. The specific heat capacities for water, it's 4.186 joules per gram degree Celsius. You could have looked it up in calories. That'd be 1.000 calories per gram degree Celsius. That's the only one I'm going to write. For aluminum, the specific heat is 0.900 joules per gram degree Celsius. And for iron, it's 0.450 joules per gram degree Celsius. So what do these mean? Well, the equation for the heat gained by each material is Q is equal to MC delta T, or using explicitly, MC times temperature final minus temperature initial. So we're going to calculate that for each one of these. So putting the known temperatures along with the unknown final temperature, I'm going to get some equations. So for water, that's going to be the mass of water, which was 125 grams, times the specific heat of water, 4.186 joules per gram degree Celsius, times the temperature final, which I don't know, and it said just putting in the known temperature along with the unknown final temperature, so I'll just put T sub F there, minus the initial temperature of 20.0 degrees Celsius. And this is the one case in life where I multiply numbers through. Notice I put in numbers and not just equations. So I'm multiplying the numbers through, and that gives me 523.25. Notice grams. Let's just show the canceling here. Grams cancels there. And in the second number, I'm going to have degrees Celsius cancel, but in the first one, I don't. So it's going to have units of joules per degree Celsius temperature final minus, and then I just multiply that by 20 to get 1046. Gotta make that more readable. 10465. And now the degrees Celsius cancel, so that's just joules, is the heat. Doing the same thing for my aluminum, I have the mass of the aluminum, which is 27.5 grams. Specific heat of aluminum, temperature final minus 20.0 degrees Celsius equals, multiplying that out, it's 24.75 joules per degree Celsius temperature final minus, and then multiplying that by 20, 495 joules. And then finally, for iron, I have the mass of the iron, which is just 20 grams, and the specific heat of iron, 0.450 joules per gram degree Celsius. Temperature final minus its starting temperature, which was 90.0 degrees Celsius, equals, and when I multiply that through, it just comes out to be 0.45 times 20 is 9 joules per degree Celsius temperature final minus, and then multiplying that by 90 gives me 810 joules. So now I just need to solve these. So I put these three equations into the equation from step B, which is the heat total. The sum of the heats is equal to the heat total equals 0 equals, and if I add these up, I have those first three numbers, 523.25 joules per degree Celsius plus 24.75 joules per degree Celsius plus 9 joules per degree Celsius times temperature final minus, add up the next column, which is 11,770 joules. Well, that equation is actually not hard to solve. This stuff here, if you add them together, gives you 557. If I add 11,770 to both sides, divide both sides by, change color for the division, 557 joules per degree Celsius. That gives me temperature final is equal to 21.1 degrees Celsius. Doesn't heat up that much. Why doesn't it heat up that much? Well, two reasons. Number one, the iron has a fairly low specific heat, whereas water has a very high specific heat. That means the water is not going to change temperature very much, while the iron has a big change in temperature. Also, in terms of mass, there is much more water than there is iron. So it has both a much bigger specific heat and a much bigger mass. In fact, we could have gone with the heat capacities. Remember, heat capacity, capital C, is equal to lowercase c times m. And so for water, that would be 4.186 joules per gram degree Celsius times 125 grams. I, of course, didn't calculate that beforehand, so I'm just going to do it real quick. For water, that's, oh, actually I did. Those are the first numbers we had here. For water, that was 523.25 joules per degree Celsius. And for iron, it was 9 joules per degree Celsius. So you can see why there's such a big change in iron compared to water in temperature. Okay, now let's go on. We calculated all of this, but now it says the change in entropy at constant temperature has the equation delta S is equal to Q over T. We could use that as an approximation. We could just say, well, let's take the average temperature between the starting and ending cases. In fact, let's do that. We would have delta S for water is equal to the heat for water. Now, did I calculate the heat for water? No, I didn't. I should have. Let me just calculate that real quick. Okay, so the total heat for the water was, I wrote, well, was 591.83 joules. The average temperature for the water is going from 20 to 21.1 divided by 2, which would be 20.55 degrees Celsius. But we need to convert that to kelvins. That's 293.70 kelvins. So over 293.70 kelvins. And so that would give us I'm going to trust I did my math correctly there on paper, not do it correctly here. I'm just going to put divided by 2.7. So that gives a change in entropy for water of 2.015 joules per Kelvin. Change in entropy for the aluminum of 27.994 joules over that same 293.7 kelvins, which is 0.0953 joules per Kelvin. And then the change in entropy, notice heat was going into the aluminum and into the water, hence those are positive. Now for the change in heat for the iron, it had heat going out, nice, 619.82 joules per Kelvin. You may be wondering, where did I get those numbers so quickly? We had already done the calculations right there in part E, so I just plugged in my temperature finals in each case to get these values. The average temperature for the iron is going to be the average between 90 and 21.1, which is (55.566 Celsius), or converting that to kelvins, that's 328.71. 71, let's just put 716 kelvins. And so that gives us a change in entropy there of minus 1.886 joules per Kelvin. Now, if we do them the proper way, that is, we take the m times c times natural log of temperature final over temperature initial. Notice the m times c's are these values. There's m times c. Those are the m times c values. And so I can just take those numbers and 3.25 natural log. Now, just a mention on units. You might have been a little queasy about my units. I use joules per gram degree Celsius for my specific heat, grams, not kilograms. And I use for temperature, Celsius degrees. The reason that was okay was because I was dealing with a change in temperature. So all my units were fine up to here, but notice when I got to the calculations for change in entropy, it's not change in temperature anymore, So I actually have to use kelvins. So the final temperature and the initial temperature, the final temperature is 21.1 plus 273.15, which is 294.28 kelvins over the initial temperature of 273.15 kelvins. And that gives 2.015 joules per Kelvin. Now let's compare 2.015, 2.015. I got the same values using the exact equation and using the approximate equation. You can see why textbooks often just go with the approximate equation for the non-calculus based class. Repeating this calculation for aluminum, we have 24.75, I forgot to put my units there, joules per Kelvin. Now, it's had joules per degree Celsius before. Now I put joules per Kelvin. Joules per Kelvin is technically the correct value. And this is the same 294.28 Kelvin over 273.15 Kelvin. And so that's going to be 0.0953 joules per Kelvin. And finally, the change in entropy for the iron will be my 9 joules per Kelvin times natural log of, and now for the iron we have to use the same final temperature, but the initial temperature is, let's see, 363.15 kelvins. And so when we calculate that, it gives us minus 1.8856 joules per Kelvin. So now once again, comparing 1.886, 1.856, yeah, they're exactly the same to the number of significant digits we have. So if we add those all together, the total change in entropy is 0.218 joules per Kelvin. Notice, as required by the second law of thermodynamics, the total change in entropy was a positive value for this exchange. Now our second problem looks short. It is a man has a body temperature of 98.7 degrees Fahrenheit and sits in a dry sauna where the walls have a temperature of 175 degrees Fahrenheit. That's actually a typical temperature for a dry sauna. What is the net rate of heating for the man? To make calculations easy, assume the man is a cylinder of height 1.80 meters and radius 0.250 meters with emissivity of 0.97. Those are realistic numbers. The man is absorbing and emitting heat due to, well, what physics? There are 3 mechanisms for heat. And this one is radiation. So the power for radiative heating has the equation of emissivity times Stefan-Boltzmann constant times the surface area times temperature to the 4th power. The surface area of the sides of a cylinder is, A sides is first the circumference, which is pi r squared. Or not pi r squared, it's 2 pi r. I'll jump ahead to the second one. 2 pi r, and then times the height. Surface area of the top and the bottom is just pi r squared. So if we put in numbers, 2 pi times 0.250 meters times 1.80 meters gives me the sides having an area of 1.5708 meters squared. And the ends having area of 0.1963 meters squared for both the top and bottom. When we add those both together, of course I kept more digits until I was done with everything. So when I add them together, I get 2 times the area of the end plus the area of the sides is 1.9635 meters squared. Remember, there are a top and a bottom to the cylinder, so you have to have 2 times the end plus the sides. The temperatures must be converted to SI units. In this case, since it's temperature to the 4th, this is going to have to be kelvins. So using the standard conversion, 98.7 body temperature is 310.21 kelvins, and the temperature of the walls is 352.59 kelvins. It doesn't seem so extreme when you look at it in kelvins like it did when you looked at it in Fahrenheit. So the net power is now just going to be calculated by putting the numbers we have into the equation from part B. Now we do have two things to worry about. We have both the man is emitting and the man is absorbing. So I'm going to calculate those separately and add them. Power emitting is sigma, or epsilon sigma, for the temperature of the man to the fourth equals my emissivity, 0.97. The Stefan-Boltzmann constant is a constant, 5.670367, times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Then the temperature of the man, 310.21 kelvins to the fourth. And I get the power that the man is emitting is 509.31 watts. Power he's absorbing is the same equation, but it's going to be the temperature of the walls to the fourth power. And so that's going to be 850.13 watts. So if I take those and take the amount absorbed minus the amount emitted, right, the one that's bigger, he's going to have a net absorption of 850.13 minus 509.31 is equal to 340, and I'm just going to put 341 watts because I think that's my appropriate significant digits here. I didn't actually pay attention to my significant digit rules throughout this problem because we have addition as well as multiplication going on. But I think that's probably the correct number. 341 watts is the net rate at which he's absorbing radiation. Now the last problem has a lot of steps. A hot reservoir at a temperature of 150 degrees Celsius has an iron cylinder of radius R equals 1.27 centimeters and length L of iron is 0.500 meters coming out of it. The end of the iron cylinder is attached to a cylinder made of aluminum having the same radius and a length of aluminum is 0.250 meters. The other end of the aluminum cylinder goes into a cool reservoir at 15 degrees Celsius. What is the temperature at the junction between the two rods? And at what rate is heat being transferred from the hot reservoir to the cold reservoir? Finally, what is the change in entropy per second for each reservoir? So I'm going to start by doing what you would do for each problem if you're a good student. There's my hot reservoir at temperature hot. Coming out of that, I have my iron rod, and then touching the iron rod is an identical in radius, but half the distance for length. It was aluminum, right? The aluminum rod, and then that aluminum rod is going into a cold reservoir. Now there are important numbers, so I'm going to put the important numbers here. So there's the distances, and of course we have the temperature hot and temperature cold already in here. Now what is this? Is this radiation, conduction, or convection? It's conduction. And so for conduction, the power for conduction, conductive heating, is power is equal to K, which depends on our material, times the area over the length multiplied by temperature difference. Because that's a temperature difference, I can leave my temperatures in Celsius. Yay! I need to look up those K values, and I completely forgot to look up the K values, or to looking up the K values. So let's just look them up real quick. K for iron is, where is K for iron? K for iron are 79.5 watts per meter Kelvin. Not millikelvin, meter Kelvin. And K for aluminum is 205 watts per meter Kelvin. Notice that aluminum is a much better conductor than iron. I found that surprising. I always thought iron was a very good conductor of heat. Okay, using the temperature X for the temperature at the junction between the two rods, the equations for rate of heating is power. To each rod is, for iron, it's going to be K of iron times, they both have the same area, so I'm going to just put that over length of iron times. And in this case, I'm going to put the temperature on the hot side first, so that will be temperature hot minus temperature X. And then I'm going to go ahead and calculate what those are. So that's going to be, for iron, the K is 79.5. Kelvin. The area is going to be, and let's just calculate the area once so I can just put the number in there. So area notice I changed it into meters to get the standard units. And of course I didn't actually calculate that in my own calculation. Equals pi is 0.0005067. Divided by the length of the iron rod times the temperature hot, which was 150 degrees Celsius minus temperature X. So that gives me 12.085 minus 0.0805 7TX. Doing the same for aluminum. K for aluminum, area over the length of aluminum, and its temperature hot cold Kelvin as that same 0.000500671 meters squared. 0.250 meters is the length here, and then the temperature X minus 15 degrees Celsius. And so that gives me got to get my sign straight here. I think I have them crossed up there. It gives me minus 6.2325. And I should have put units there. That would be, notice the meters cancel. I have watts per Kelvin. So watts there. Watts plus 0.4155. And this should be watts per degree Celsius. I changed from Kelvin to Celsius because I'm multiplying by Celsius. So I have those two equations. The power going through the first cylinder has to equal the power going through the second cylinder. So I'm going to set those equal to each other. So I'm going to have power of iron equals power of aluminum, which gives me 5. I wrote as a J in this handwriting. So if I take that and I move the things with temperature to the right side and the things without temperature to the left side, I will get a simpler equation, and I actually didn't write the intermediate. 12 plus 6 is 18, so that's going to be 18.3, let's see, 175 watts equals 0.49 2 into 1, 2. I should write this down. 4, 9. Oh, nope, it's going to be 50 because the carrying. But no, that's right. 0.49, and then I have 5 plus 0, and then a carried 1, so 6. And finally, okay, I should have done that beforehand. Dividing across, that is dividing both sides by the we get temperature X is 36.9 degrees Celsius. So the temperature at the midway point degrees Celsius right there. This was 15 degrees Celsius. This was 150 degrees Celsius. This aluminum is a much better conductor of heat, and that was a shorter distance. So that's why the temperature between the rods was so much closer to the cold temperature than the hot temperature. Okay, putting Tx into either of the equations in part C, calculate the rate of heating. So you just put in the temperature we calculate into either one of those equations, and you get that it is 9.11 joules per second. At constant temperature, the change in entropy is easy. It's just Q over T. So calculate the change in entropy per second. So notice these were power. That was joules per second. So in 1 second, Q is equal to power times 1 second equals 9.11 joules. So delta S from the hot reservoir, heat is leaving the hot reservoir, so that's minus 9.11 joules. Divide by the temperature. Now, because it's not temperature change, I must shift to using kelvins. So that's 150 degrees Celsius plus 273.15 gives me 423.15 kelvins. And so doing that calculation, my change in entropy for the hot side is minus 0.0215 joules per Kelvin. Doing it for the cold side, delta S cold is equal to, now this one, the heat is coming in, so it's positive, and the temperature is only 15 degrees Celsius, which is 288.15 kelvins, and that's equal to a positive 0.0316 joules per Kelvin. So the net change in entropy is just adding those two, 0.010, yeah, do it right, 0.101 joules per Kelvin. So there's my net change in entropy. Once again, as required by second law of thermodynamics, the change in entropy for this process was positive. All right, hope that helped. And recording.